you get to it, we'll talk about some hyperbolic trig functions too. If we don't get to it today, we'll get to it tomorrow for sure. And like I reminded you yesterday, if you don't already have your Chapter 8 notes printed out and just kind of stowed in your bag for later, I think for sure we'll get to it tomorrow. So I don't think we'll get to it today though. Okay, so inverse trig functions is basically just a kind of a different class of functions we haven't looked at yet this year on how to deal with derivatives and integrals yet. So I'm going to list out these rules for you, and then we'll kind of work on proving one or two of them for you. So the bottom line is you kind of have to have these memorized, but the path that you take to get them memorized or rememorized is up to you, right? So let's just do a little remembering or perhaps learning for the first time what these are. So the derivative of arc sine of u over a, where we want to remember what u typically stands for. U normally stands for a function in terms of x. So that'll be true of all these. So it's some function in terms of x. And here is the derivative, unless any of you think you remember it. Okay, fair enough. So the derivative of arc sine of u over a is equal to u prime over the square root of a squared minus u squared. This more or less comes from trigonometry and the Pythagorean theorem. Perhaps you can see sort of the Pythagorean theorem in the denominator there a little bit, kind of, sort of. Parts of it anyway. We'll get to that in a little bit. Then the derivative of arc cosine, hopefully not surprisingly, is just like the derivative of arc sine, except it's negative. That's it. So it would be the opposite of u prime over the square root of a squared minus u squared. That's a squared. There we go. And then finally, arctan is a bit different looking than those two. It is still a fraction. The derivative of arctangent of u over a is equal to u prime times a over a squared plus u squared. Again, so I think if I remember correctly, if you were to peek in your book, like your textbook or look at the ebook, I think you would see slightly different variations on these based on a slightly different setup expression. They all are true and correct. What I feel like is that this works better with what we're about to do in 5-7, like this line of thinking. So that's why I've presented it the way that I have. So down below there I say it might be easier to learn how to derive these instead of just memorizing them. I use the word might. If you're a great memorizer and you just memorize it, that's awesome. I would at least, even if you are a great memorizer, I'd at least like to show you where one of these came from. We can do more than one if you want. So somebody pick one. Which one do you want to see? Arc cosine. Fair enough. So let's go down here, and I gave myself a little bit of space to do that. Oops. So I am going to write, starting off, I'm going to write y equals arc cosine of u over a. So if I set it up like that, knowing that u is some function in terms of x, and I'm trying to find a derivative, wouldn't it be fair to say that my goal is to find dy dx? Okay. But if we think about this, if we're going to try to find dy dx, we immediately run into the issue of, we're trying to prove the derivative of arc cosine is something. And so, the right side, we'd just be doing the derivative of it. So I don't know that this is going to prove anything unless we write it in a slightly different form. If I were to write this implicitly by doing the cosine of both sides, I would get cosine of y is equal to cosine of arc cosine. Of course, that's just going to cancel out. We end up with u over a. Let's keep in mind that y is a variable, u is a variable, and a is a constant, right? Kind of the standard convention of letters at the start are constants and letters at the end are variables. Okay, so now we do know what the derivative of cosine is. And so let's do d dx of everything. We'll use implicit differentiation to do this. So if I do d dx of everything, so d dx of all that stuff in the parentheses, what do you guys think d dx of cosine y is? Just using the old, right, using the old implicit differentiation, Blake, you are correct. Negative sine y times dy dx. It might be helpful to think of the u over a slightly differently. You might be tempted to use the quotient rule here. How could we mentally rewrite u over a to make it not be a quotient rule? Well, but the a is a constant.
1 over a times.
Yeah, let's make just like separate them with a fraction and a numerator. So yeah, 1 over a would just be a constant multiple and then times the variable u. So like let's mentally think of it like that. So if we do think of it like that, then what is the derivative of the constant multiple 1 over a times the variable u?
1 over a u prime.
Yep, 1 over a. And you could write du dx or u prime. I like your idea of u prime. That'll be a little bit easier to deal with. Let's keep in mind that that is derivative with respect to x. Okay, so remember our goal at the start was to find the derivative, and specifically here dy dx. You see it right there, don't you? So I've got dy dx equals 1 over a. I'm going to divide both sides by that negative sine y, so that would be u prime over negative sine y. I'll put it over there. So let's just do a quick comparison with what you have written above. This is starting to kind of take shape, right? You can see that the right side wants to be negative, so that's good. And the top wants to be u prime. So if you look at this, really, we have the top proven, don't we? But the denominator, not so much, right? It's a sine of y. That's not so good. So I'm going to write, I guess I'll do this. I'll write one more step. Maybe you guys already did this. I'm going to write dy dx equals negative u prime over a sine of y. So again, I'm just reiterating, I've got the top pretty much figured out. Denominator, not. Okay, so any ideas on what I could do to deal with that denominator? The a might be okay, I don't know, but I definitely, the sine y, right? That's really the glaring thing we got to deal with. Any thoughts on what I could do to deal with it? How can I make it go away? Replace it with something that I want. Think deeply. Let me ask you a little bit of a helping question. Sine of something, right? Isn't it actually asking you to do something, kind of? What is it asking you to do? Sine of some thing. Like if you try to explain this to an Algebra 2 trig student, like, why? Couldn't you say that sine is like implying an action, like it's saying, do this? What is it implying that you do? Opposite over hypotenuse of a triangle. Isn't that what it's saying? Find the opposite, find the hypotenuse, and make the ratio, right? Okay, so, great. Where's the triangle? Where's the angle? Y is the angle, yep, but we need to be, you're 100% right. But in order to figure out the whole opposite hypotenuse routine, we need to be able to like think of it in terms of like y is really this, like something bigger. Yeah, that's right. Okay, so now we're starting to get there. I think you guys realize this. Isn't arc cosine of u over a describing an angle? I mean, it's not as direct as saying, hey, the angle is 27 degrees, but it's describing an angle. Like arc cosine of u over a is an angle. It's not refined all the way to what we're used to seeing, but that's all it is. It's just an angle. So what we're going to do is take the idea of a triangle and the opposite and the hypotenuse, and we're going to try to build this out. So I'm going to maybe come over to the side here to do this. And I'm going to build a triangle. based on the little statement up there that's highlighted. It's a right triangle. It's got a little excessive leg there, but that's okay. We're told that the angle y, I'm going to put it right here, has an arc cosine of u over a. So that means which side is u? The which side?
Adjacent.
The adjacent side, yeah. So that means this side is u, and the a goes where?
Hypotenuse.
All right, now we're starting to go somewhere with this because down here, I'm supposed to do sine of that angle. And when I think, all right, cool, I'll do sine of y, I know that, SOHCAHTOA or whatever, sine is opposite. There's no opposite side, it's blank. So we use the Pythagorean theorem. Okay, so Pythagorean theorem, I don't know what we call that side there. Well, I don't know how much detail you want me to go into here, but it'd be u squared plus the missing side squared equals a squared. Oh, that's not what I wanted to do. Reverse that. There we go. A squared. So s squared is equal to a squared minus u squared, meaning the missing side is square root, right? We'll take the positive side. So square root of a squared minus u squared. That make sense? So now we're free to do the sine of that angle. So this will actually take us right to the finish line. Dy dx equals negative u prime over a times opposite over, look at that, hypotenuse. See ya later. And we got it, don't we? Okay, so I love doing that because whenever we could do stuff like that, I'd love for you to know where things come from, wherever possible, where time allows or whatever strategy allows. Of course, this strategy, like if you really wanted to push yourself a little bit, if you were a student of math, you certainly could try to do this with other ones too, right? You could try this for sine. I think you'd find it to be quite similar. Tangent's a little bit different. There's formulas for derivative of arc secant, arc cosecant, and arc tangent as well. They get a little more complicated, and we're not required to do them, so I don't think we're going to go there. They're very uncommonly used. But if you're a math student, you're like, you know what, I want to challenge myself a little bit, you could try those too. They're listed in your book, and you could try to arrive at those using similar type strategies as these. So anyway, when time allows, I find those things interesting and fun. Hope that was okay. Blake, thanks for picking that one. Do you guys have any questions? I don't think that I would ever directly ask you to do that, but I think all those skills are things that are certainly within your grasp. I have no doubt you can do that sort of thing if called upon. All right, so let's leave that alone for now. Let's practice these a little bit. And the practicing would be here. So at this point in the game, oh, come on. There we go. There's 1, 2, and 3 right there. At this point in the game, you've got formulas for these, right? And so really where this comes down to is if you can remember the formula and correctly identify the u and the a, this comes like a very formulaic, plug it in, finish it sort of a proposition. So I'll give you that chance to do it that way, and then we'll check your answers. All right. McKenna, would you identify in number 1 as the u?
2x.
2x definitely works there. So if that's the case, what's your a value?
1.
1. All right, so 2x is really 2x over 1, u over a. It fits the pattern. I think you've done a nice job. And then it's really just a matter of fitting it within the formula, right? So, I don't know if it would be helpful for you to write it out here as well, but maybe you could write u prime knowing that that's part of the formula, right? So in this case, u prime is 2. And I think you've got all the little pieces where they're, just got to put them where they're supposed to go. So McKenna, I'll let you finish this one off. What do you have for that derivative?
I got 2 over the square root of 1 squared minus 2x squared.
So 1 squared minus 2x, I assume in parentheses, right?
Yes.
Squared. Okay, yeah. That works just fine. Obviously, you can simplify that a little bit. If you wanted to, you could put that as 2 over square root of 1 minus 4x squared. That would work just fine too. Pretty good? Okay. Alyssa, how about number 2? What was your u and your a?
My u was 3x and a was 5.
Okay, and then did you write out like a u prime as well, or did you just kind of do that in the middle of it?
But it would be 30.
Yep, okay. So if we do that, now it's a matter of plugging in. Let's hear what you got.
15 over 25 plus 9x squared.
Nicely done. Simplified. Didn't have to do that, but you did. You did it correctly, so that's great. Of course, the top is 3 times 5, right? U prime times a. Sometimes folks will forget that arctangent has that extra factor of a in there. And again, where does that come from? You can do a little proof. You can see where it comes from. It comes from Pythagorean theorem again. All right, and then finally number 3, Sean. What do you think about that one? What was your u and your a for this? U is x to the 1/2. And a is 1. Did you write out a u prime for this one? You could do it in the middle of it. I mean, you don't have to do that, but I think identifying the u and the a is key. So why don't you, would you mind sharing what you did for an answer?
Answer is negative x to the negative 1/2.
Can you say it a little bit louder?
Negative x to the negative 1/2
Negative x to the negative 1/2.
over 2 roots 1 minus x.
Say square root of
1 minus x.
1 minus x, okay. What do you think about that? Yeah, so he got 1/2 x to the negative 1/2. Obviously move the 2 down, that works. You could manipulate this as well. You could move that x to the 1/2 down. I mean, there's all kinds of ways you could do this. Negative 1 over 2 root x root 1 minus x. Sorry, that's right on the bad spot there. Then you could even distribute the root x. You could get negative 1 over 2 square root of x minus x squared, right? If you multiply that root x throughout the other radicals. So, I mean, there's lots of ways that could look. Sean's version obviously is correct. We could stay with that if we want to. So, any questions? Okay, fair enough. Well, one of the reasons that we do this is so that we can do what comes next. So let's flip over to 5.7. In 5.7, you will see that we've got integrating with inverse trig functions. So this is not integrals of inverse trig functions, just integrals that will involve inverse trig functions. So these are integrals that are in the past. If they would have shown up, we would have said, oh gosh, we don't know how to do that. It's not the right form. It's not an ln. It's not a flip it up type of a deal. And just so you guys know, in chapter 8, which we're going to do next, there will be several other forms. Or prior to this, we would have said, oh, we can't do that. Well, chapter 8 will introduce a few more skills where, oh, we can actually do that. All right, so the key, in my opinion, is to recognize the pattern based on your experience, what we saw in 5.6. And if you do recognize the pattern, you would eventually see that the integral will result in, as you might guess, an inverse trig function. All right, and then of course, if your derivative skills are really good, you could always check these by doing a derivative. Although I feel like they're so tightly, tied together that it would be really hard to get this wrong and do the derivative correctly unless it was just some minor detail. Does that make sense? But the derivative and the integral should go together really well. So take a look at that first one. Integral of u prime over the square root of a squared minus u squared. The hope is that we would look at this and say, oh, I've seen that somewhere before. That's,
Sine u over
yeah, it's the derivative of arcsine, right? And so wouldn't the integral just undo the derivative? I suppose if you wanted to, you could almost think about it like this. Think about this. You could say this is equal to the integral of the derivative of arcsine of u over a. Make sense? It's the integral of the derivative of arcsine of u. So wouldn't the integral and the derivative do battle and cancel each other out? So, of course, you just end up with arcsine of u over a plus c. Is that a good way to explain it? Does that make sense? But don't you have to recognize it in order to see that? Okay, so I'll write it out the official way. We don't need all that stuff. Once you recognize what it is and your du is correct, everything is there, it is just arc sine of u over a. Okay, any questions? All right, and what's the other one? It's arctangent, yeah. So you'd go arctangent of u over a. They both have plus c's, and we call it good. Okay, so recognition, that's like kind of a loaded word, isn't it? What does recognition imply? Okay, come on. Our first example, using these ideas, and maybe we can do this first one together, and we can kind of help you recognize a little bit, and then we'll build to a little crescendo at the end. We'll kind of work through these. But what I would like to do, can you suspend your disbelief for just a brief moment? I would like to treat number one as if it was a quiz question or a test question. Okay? So let's say number one is completely out of context. It's on the AP test. It's on one of our quizzes or something. It's on some review. You've never seen it before. You look at that, and here's what I'd want you to recognize. Number one, the integrand is a fraction, right? And that's always cause for pause and concern a little bit. So I told you this in the past. I'll tell it to you right now. I think when you're looking at these, the very first thing you should think about is, if the integrand is a fraction, is it ln? So is the derivative of the denominator the same thing as the numerator? And that hasn't been a big deal in the past because usually Timmy just messes up and we fix it and move on. We're done, right? In this case, I don't think it's going to work that way because if you look at the denominator, the derivative of the denominator is going to be a chain rule, right? It's going to be 1/2 times 4 minus x squared to the negative. I mean, you can see immediately the top is unfixable from that perspective, right? So it's definitely not natural log. One of the ones that people seem to always forget about, don't write this down, is flip up. Like what if we flipped up and wrote that? This is a very possible strategy. But in order for this to work, you got to be able to use u substitution or see that Timmy messed up by just like a little constant multiple. You can see the inside is 4 minus x squared. What's the derivative of the inside? And so that factor should be right there or right there or something. And there's nothing there other than like a 1. And so the fact that he's off by a -2 is not a big deal. The fact that he's off by an x means that it's some other form. So flip up doesn't work. And so if you follow this line of thinking, you'd say, is it ln? Nope. Is it flip up? Nope. The next thing you'd think of, is it an arc cosine or arc sine, arctangent? Is it an inverse trig function? So this is where we'd end up here. We'd say, all right, fine. It's not ln. It's not flip up. Bless you. If it's going to be an inverse trig function, based on your experience, which one might it be?
Arc sine.
And what element or what symbol tells you that arc sine is realistic?
Square root.
The square root and the whole difference in the denominator, right? So a couple of elements there tell you, yeah, it very well could be arc sine. So if that's going to be the case, let's see if it fits. Let's identify what would have to be our u and our a, and then based off that, our u prime. So what do you guys think? Can you identify what the a and the u would have to be?
X.
U would have to be x, and a would have to be 2. Okay, so then u prime would be 1. Okay, so we try to build this out, and we think, all right, we want this to fit this pattern of integral of u prime over the square root of a squared minus u squared. Wow, this fits perfectly, doesn't it? If a is 2, then a squared is 4. If u is x, then u squared is x. We got the difference, we got the square root. Even the top, like Timmy didn't mess this one up at all, did he? The top is supposed to be a 1, and it's a 1. So based on that kind of reasoning, we could immediately go to it and say that the antiderivative would be arc sine of our u, which is x, over our a, which is 2. Throw in the plus c for good measure, and we got it. Make sense? Okay, good deal. Well, why don't you guys try a few more here? Definitely try number 2. We'll look at maybe some other ones also. And then we'll, like I said, we'll kind of build to a finish for this. Let's see here. 2, 3, 4. Let's do 2, 3, 4. I think those are all pretty good. of, if this were out of context, what would you do? This looks a whole lot more like ln, doesn't it? Can you see how someone might, and most definitely has in the past, take this and be like, oh, ln, done. You see how somebody can make that mistake? If they just kind of conveniently ignore the squared, then it is ln, right? So you want to be really careful with that. So with this one, you do look at it and say, hey, the derivative of the denominator is 18x. The top is just a 1. And so it's definitely not ln, right? Because you're off by a factor of x. Same idea with flip up, right? You'd actually end up with another problem with flip up. Do you remember this one? If you did integral of 4 plus 9x squared to the negative 1, not only are you missing a factor of 18x, but when you do the power rule, division by 0, right? You get something to the 0, which is not a big deal, but over 0 is a big deal. So that one doesn't work for lots of reasons. So then you finally end up at maybe it's an inverse trig function that we're heading towards. So if we're going to do that, Caroline, what would you use for your u?
3x.
3x is right. How about your a?
2.
Okay, so then u prime usually comes into play here. So your u prime would be 3. Looking at this, if it is going to be an inverse trig function, which one would you kind of narrow in on?
Arctan.
And what tells you that arctan is realistic?
There's no square root in the denominator.
Yeah, and the plus.
Plus.
Yeah, both of those factors should lead us to think that at the very least, it's not arc sine or arc cosine. All right, so then Caroline, what'd you get when you? Well, I don't know. Did you do full-on u substitution here? What? How did you? I'm just kind of curious because I know that you typically don't do the Timmy thing.
Yeah, I usually just solve for 1/3 du equals dx.
Okay, so all right, so you do. So you're doing du equals 3 dx. Okay, so like that. Okay, so then substitution-wise, let's build it out. That would look like what? Du over 3?
Or yeah, 1/3 outside of
How, so then, the 4 is just 2 squared. So what, I'm just kind of curious how you do this. Because I am very much in the habit of Timmy messed up the chain rule and just blast through it. So
Yeah.
share what you do.
Well, these confuse me a lot because Mr. Lauer never really fully explained why you multiply by another half, because it ends up being 1/6.
And that's what I was going to ask you about. I totally get the du over 3 thing, but how did you account for the a?
Yeah, he told us to multiply by 1/a after you do that.
Okay, so that's very formulaic, right? That's sure. So that's like a very formulaic way of looking at it. In fact, I think that's what your book shows, that you just always multiply by 1/a. Can I show you what I do?
Yeah.
Because for me, this helps me have a process instead of and don't forget the 1/2. Okay, so let's see here. So we set things up exactly the same way. I would recognize arctan just like you did, but in my head, what I'm thinking about is the derivative, right? I'm thinking, okay, the derivative of arctan of u over a is u prime a over a squared plus u squared. And if somebody said, well, why is it u prime a over a squared plus u squared? We'd go back and prove it the same way we proved the arc cosine before. So I'm thinking about, okay, so I know that it has to be u prime a over a squared plus u squared. So what I would do is I would say, all right, u prime is 3, a is 2, so u prime a, I guess what I would do is I'd say u prime a is 6. And I'd say, well, the top has to be 6, but it's not, it's a 1. So I'd multiply the top by 6, and I'd multiply the outside by 1/6. And then I've still got the, 2 squared plus 3x squared routine. That's how I deal with it. I don't know if that makes any more sense to you, but for me it's like a thought process instead of a don't forget to do this sort of a thing. So I was curious how you dealt with the a. Okay, so then we can just go straight to the answer, right? And you probably got this in spite of maybe I'm not sure where how that all works. You went straight to arctan, right? So arctangent 1/6 arctangent of 3x over 2, and then plus c. Okay, is that good?
Yeah.
Okay.
It makes more sense. Because last year, you're just just multiply.
Right, use the formula, and I get it, and that's a standard way of doing it, but for me, I ask the question as much as you guys do, why? Why is it there? Why do I have to do it? Because I feel like if I can understand why, I have a better chance to remember later on when I'm in the middle of some assessment of like, oh gosh, do I multiply by 2? Do I divide by 2? But more important is why, and if you can kind of understand the why, then you got a good shot. So, okay, well, we'll keep working on that. I'll try to think of a better connection for you to try to connect the two of, how do I connect U substitution with the whole Timmy messed up the pattern and go with that. All right, so number 3 is another layer down, right? Caleb, what'd you think here? What'd you identify? It's not ln, right? It's not flip up. It leads to some kind of an inverse trig. What'd you do with it? What'd you identify?
I decided it would be arctangent.
That seems logical, right? Because the no square root, no plus sign, or no minus sign thing. Yeah, okay. So then keep going. What'd you do from there?
So I realized the top was off by a factor of 10.
Okay, let's go deeper. You're right. Let's go deeper as far as the why. Like where, and this would be where we could help. Like, if Caroline was like, 10, what? Right? If somebody's like, where'd you come up with 10? Let's talk about why 10.
So the u is x squared and the a is 5.
Okay.
So that's the square root of both of those bottom.
Yep, 5 squared is 25. X squared is, yep, x to the 4th. Totally agree. Keep going.
And so because with our arctangent, you have to have u prime times a
Yep.
in the top.
Yep.
We already have the x up there,
Mhm.
so it's off by a factor of 2 for the u prime,
Mm-hmm.
and it's off by a factor of 5 for a.
We're missing both factors.
Right.
Agreed. Okay, so that's where the 10 comes from.
Mm-hmm.
Does that make sense? Okay. So, yeah, let's fix it, right? That's what we need to do. If we're going to do the whole Timmy messed it up thing, we fix it. But then to fix our fix, we got to do what?
To multiply by 1 over 10 on that side.
Exactly right. So now it perfectly fits the chain rule pattern for arctangent. We jump straight to the answer. What would your answer be?
1/10 arctangent of x squared over 5 plus c.
And you even remember the plus C. You're the man. Nice work. Okay. You have any questions? All right. That's good to hear, or not hear. Number 4. Blake, what you got?
All right. So, I got that being arc sine.
Yep.
So the top, well, actually, I'll start with my u. I
Mhm.
said it was 14. And my a, I said it was 3. So u prime would be 4. And so the top has to be u prime. So you got to top by a factor of 4. So you got to multiply by 4, and then multiply the outside by 1/4. And then my answer was 1/4 arc sine of 4t over 3 plus c.
You are also the man. Correct with plus C. Okay. He did a really nice job of explaining it. I don't know if I can add a whole lot to that, unless you've got a question. All right. Fair enough. 6 and 7. 5 and 6. I can count. Contrary to the evidence, I can. On a good day. Number 5. So let's go through the process here. Here is where there's like a little layer of challenge, and I'll just be straightforward with you. In chapter 8, I'd say chapter 8 potentially adds another layer of challenge to a question like 5 or 6, because it's going to come down to little details. Like, for instance, if in number 5, instead of the 34 being a 34, if it was a 7, this would take on a very different look. If it was maybe a 5, it would take on a very different look. So we're going to parse it out even more detailed in chapter 8, just like the nature of how the numbers in the little denominator there work out is going to change things significantly. But for now, we're not going there. We'll go there soon. But for now, what we would do is we'd say, all right, it's a fraction. Yay. Is it ln? Emphatically no, right? I mean, the derivative at the bottom is 2x plus 6. And I'm really hoping that none of you thought, oh, well, why don't we just go, right? That's like really bad. So we're not going to erase that really fast before somebody sees that. Maybe I'll edit the video or something. I'm kidding. You can't do that, right? So it's definitely not ln. Flipping up is going to cause similar issues, even worse, really. And so, yeah, if you're doing this realistically, you'd say, okay, it's not ln, it's not flip up. The only thing I'm left with at this point would be arcsine, arctangent kind of stuff. And then when you look at the denominator, it doesn't fit at all. There's no square root. So you're like, all right, cool, it's arctan. But then when you look at what's down there, it's not a squared plus u squared either. You remember what to do, veterans? Got to complete the square on the denominator. Got to complete the square. So completing the square takes something that is not a perfect square and turns it into a perfect square. So we'll do that off to the side. So I've got x squared plus 6x plus 34. The way that I would note this is I would group the x squared plus 6x with some parentheses, but I'd leave a little bit of space on the end. And you identify your b. In this case, the b is 6. You remember what you do with the b?
Divide by 2 and then square it?
In that order, yes. Cut it in half and then square it. So what results from that?
9.
Yep, and so what you do is you take that 9 and you add it to the inside of the parentheses. Of course, your math instincts have got to be saying, wait, no, you can't do that. You can't just like add 9 to an expression and say it's the same thing. So how do we balance it?
Add 9, subtract 9.
Subtract 9 from the outside. No, it's not an equation, so we can't like add 9 to both sides. We have to basically add 0 to the expression. So plus 9 minus 9 is a really intelligent 0. So now we factor, and now it is nice and factorable. Not only is it factorable, it's factorable as a perfect square. So this factors as x plus 3 quantities squared. And look at that, 24 minus 9, or 34 minus 9 is another perfect square, plus 25. So that means the denominator is that. That's just a different form of the denominator. And you could FOIL the x plus 3 back out and see that it really is the same thing. So what I think I'd do is I'd come back over here. I'd get the 6 out of there for one thing, but I'd rewrite this as 1 over x plus 3 squared plus 25. At this point, we should be able to look at it and say, well, it didn't really look like arctangent or arcsine before, but now it pretty clearly looks like what? Yeah, it's definitely arctangent because we've got the plus in the denominator and there's no square root. Okay, so if that's going to be the case, Cameron, what would your u need to be?
It'd be x plus 3.
That's right. So x plus 3, and Cameron, how about your a value?
5.
All right, and then for good measure, let's throw the u prime in there also.
1.
It's just a 1. Okay, good. So then what I would do, here's how I would handle this. I look back at the top and say, or look back at the integrand above and say, well, it's going to be arctan. The top needs to be u prime times a. So u prime times a is just 5, and it's only a 1. So Timmy messed up. We'll step in and help out a little bit, fix it, multiply the top by 5, and then we'll divide the outside by 5. So when you do that, you end up with 6/5. It is arctan. Everything fits nicely. Arctangent of x plus 3 over 5 plus c. All right. You guys have any questions about that? We just hit our time, didn't we? Isn't it 50? I thought we'd finish. That's okay. We'll just do this tomorrow. Have a wonderful rest of your day. Tomorrow we'll break out the hyperbolic sine and cosine. Pretty simple. We'll keep it real simple for you. But I hope your day is great. Don't forget chapter 8 stuff tomorrow too.